Alright, so my name is Drew Sheriff, and I'm talking about Lab 3 today. So basically, the purpose of this lab is to demonstrate parallel and perpendicular forces using glow script. The forces parallel are with the momentum, and the force perpendicular, the force is perpendicular to the momentum. So the models used, so on the left we have the model of just the planet and the black hole, and that was used to find the mass of the black hole. And on the right we have model of the spaceship leaving the planet and going around the black hole. And we use that to find the initial velocity required for it to escape the black hole. Assumptions are there's no outside forces on the black hole planet / ship system, and there's no drag. The main fundamental physical principles in detail are the velocity update formula, position update formula, force of gravity is equal to negative g times mass divided by position vector squared. The force is equal to change in momentum divided by change in time. So a brief preview of the main results. I found the mass of the black hole and the velocity that the ship requires to get off the planet. The system is the black hole, the planet, and the ship. The surroundings are the rest of space. The initial conditions are the planet is orbiting the black hole, time is 0, and the black hole is the origin. Alright, the code and details explained. So on the left, we have the momentum vectors, and then we have change in velocity, change in momentum, and then we defined change in momentum divided by change in time is delta p divided by delta t. Net force is equal to dp dt, and then we were calculating dp dt parallel to the momentum. So the momentum unit vector is that line that says vector, xvel, idx, etc. And then below that we have momentum, magnitude of momentum divided by time. Then we have on the bottom the dp dt parallel is equal to magnitude times the unit vector. And then below that we have f net parallel is equal to dp dt parallel. dp dt perpendicular is equal to dp dt minus dp dt parallel. And Newton's second law used to calculate f net perpendicular is just f net perpendicular is equal to dp dt perpendicular. And at the bottom, here's the most important part, we have the formula that allows us to get the mass of the black hole. So it's the magnitude of force times the position vector squared divided by g value times star mass. Thank you. And on the right, we have position vector for we have radius of the planet to black hole, and we have the force of the black hole and the planet, which is just using the force of gravity formula. And then we have that a few more times for different scenarios. And then at the bottom, we have the velocity update formula and the position update formula for the planet and also the ship. The similarities and differences between the models are that both models involve the same solar system, same black hole, same planet, but the one on the right has the spaceship leaving the planet. That's where we calculate the initial velocity. Potential source of error are in coding accuracy, in plotting the scale, and in rounding. What does it mean? So the difference between net force and rate of change of momentum is that net force describes all of the physical principles occurring. Is there gravity? Is there drag? Is there other forces? Is there spring force? Blah, blah, blah. But the rate of change of momentum is showing us what those forces do. Like, does it make it move? Yes or no? We can't tell what forces are acting on the system just by the rate of change of momentum, but we can tell what the system is doing. Thank you.
To get the spaceship to orbit the black hole, you need a velocity that allows it to get off the planet, but still be weak enough to not be able to break free of the black hole's gravity. So you have to find a number that would work with that. I was unable to find a scenario where that would work for my system, but maybe yours can.